So here we are, about to embark on a grand adventure, this time to look at a fault. So geomorphology is often controlled by the underlying geology. So that's why we have to learn about plate tectonics, why we have to learn about the different rock types, we have to learn about folding, we have to learn about faulting. So today we're going to look at the last item on that list, faulting. So about 70 kilometers from the rock and sky base is a fault. In fact, there's a lot of them around, but there's one well exposed in a road cutting, so we're going to go and look at that, a normal fault where younger sediments have been downfaulted against much older sediments. So it's a fantastic example for us to demonstrate and bring this subject to life. So watch to the end and I will tell you about the amazing resources and courses that are available to you, and you wouldn't want to miss out on that. Alright, ladies and gentlemen, boys and girls, we're here to look at a geological fault. So on my left, your left, my right, is 1.1 billion year old granites. So I'm going to go with a hammer and hack into this granite. So this granite's pretty rotten. It's highly weathered. We're in quite a subtropical humid environment here, so it's rotten. But this whole valley down to my right, your left, is full of this. It's the granite and gneiss basement of an old metamorphic terrain. And this line that you can see running down here is actually the fault plane. So this fault plane goes up and daylights, and it will continue down under the ground and down into the valley behind. On the right hand side here, where I'm bashing with a hammer, is what's called fault brechia. So this is a tectonized, mashed up, crushed, mangled mass of rock. You can see, if you were to look carefully, I don't know if you can see it with the camera, there's lines in here where it's all been chewed up and mangled up. Alright, so now we've got granite, we've got fault breccia, and then we're going to walk up and we're going to be looking at what's called the Tillite. So this is a glacial deposit and it was laid down about 290 million years ago. So it's 290 million years compared to 1.1 billion years. But how do we get one sitting against the other? There's only one way to do it, and that's to fault the younger material down against the older. And that's what's going on here. We've got this fault. So this is the old rock and this is the younger rock. Because of those movements, obviously there's huge stresses going on the Earth's crust. And that's why we've got this mangled up breccia, because there's down drag and friction and heat and everything else involved, and everything just gets chewed up and mangled up. Moving upslope a little bit in the direction of the Tillite. This is Tillite. I'm on Tillite now. So there's a transition. This looks like chewed up granites, and then this is the Tillite. And I know it's Tillite because it's got all these little clasts in it that would lay down in a typical glacial deposit. There's little core stones here, and core stones and core stones and core stones. So this is Permian to Carboniferous Tillite laid down when Southern Africa, and in fact Gondwana, was at the South Pole. Alright, so let's move up the slope. Again, more Tillite. And then there's this line here, which is also part of the fault, and I'm chewing it out with a hammer. And you can see I've got some clay out of this fault zone. So the rock starts to rot. That's because of the preferential flow paths for the water. And so there's lots of clay in here. So we're actually we're kind of more in a fault zone here rather than a fault plane. Just to my right here, I can see the slope here, and it's covered in soil. But about 15 meters slightly further up the slope, we're going to get a look at the Tillite itself, the weathered material. Alright, so I'm standing now on this Tillite, the 290 million year old glacial deposit. So this is also very, very weathered now, crumbling away under the pick. But the reason how I know it's Tillite is because I've been looking at this stuff for many years, but also it's got core stones in it. And sometimes you get these things up to 20, 30, 40 centimeters in size, where it's all the debris that the glaciers have gouged up and put through the mill of the glacial mill. But there are little core stones in here, like there's one here. I can just dig it out. And this is the stuff that hasn't been ground up. So, and then when you see the stuff in the fresh state, it's actually a blue, hard rock. Good enough to crush and make stone aggregate for roads and concrete work, so it's pretty useful stuff in its fresh state. But here it's very weathered, and partly because it's close to the fault and it's had all those tectonic effects where the water's got in and allowed it to weather. To make this really loose brown, it's not a residuum, you can still see the rock structure here, very evident, but it's certainly not fresh material. Okay, so I think we're done. We've had a look at a little fault. So we're pushing to get our rock and sky courses out by early 2022. So I know some of you might be watching this later on, but the message is still the same. So being earth scientists, we're looking at what we know best. And so the first course we're going to do is plate tectonics. So we're going to stand on Indonesian mountainsides, Himalayan mountainsides, and marvel at our world. So plate tectonics affects our world in ways unimagined. And then we're going to look at the Rock Trinity, which is closely associated with plate tectonics. So that's igneous, metamorphic, and sedimentary rocks, and how those are formed in amazing environments. Then we're going to look at how the Earth's crust is lengthened or shortened through faulting and folding. So faulting can lead to the formation of ocean basins, and folding can lead to the formation of massive mountains like the Himalayas. And then something that geologists don't really spend much time with, but I know it's an integral part of the geomorphology course, is rocks and rock weathering. So we'll look at how rocks break down. They get thrust up into the teeth of the gale, the snow, the ice, the rain, the frost action, the physical weathering that breaks the rock down, and then the more subtle way that rocks get weathered, where the rain and the moisture gets in and rots the rock. So we'll look at those, and then how the rock is eroded away, that weathered material transported, and ultimately might form a new rock, a sedimentary rock, which then can get metamorphosed. So if you are interested in these courses, that will really, really support you in your teaching endeavors or in your homeschooling, then click on the link in the description below and leave us your email address, and then we'll keep you informed on when we launch the courses. So you won't be wanting to miss out on these. So we look forward to seeing you on the other side. And remember, before you go, give us a like, leave your comments in the comments section below, and share with your colleagues if any of this has resonated with you. So to recap, we've got the Natal Metamorphic Province, granites and granite gneisses. We've got the Natal Group Sandstone on top of that. And then we've got the Dwight-Catilite on top of that. So this bottom one is 1.1 billion years old. We've got the Natal Group Sandstone, which is about 450 million, if I remember. Then we've got the Dwight-Catilite on top of that. It's about 290 million years old. To get tillite against granite, we have to have a fault to fault it down. In between is what we haven't seen, Natal Group Sandstone. So it's a very thick sequence of an amazing accumulation of very hard rock sandstone with some subordinate shales and mudstones. Okay, so that's the end of that. We've now learned a little bit about a fault. We've seen one in real life. I hope you all learned something on this fabulous 31st of October 2021, Halloween. Happy Halloween.